Thanks, Oliver. All right, good morning, everyone. It is my great pleasure to introduce Professor Katherine Kuchenbecker while she sets up. Katherine is the director of the Haptic Intelligence Department at the Max Planck Institute of Intelligent Systems in Stuttgart. Can you hear me? Now you can hear me? OK, I will start again. It is my great pleasure to introduce Professor Katherine Kuchenbecker, who is our first keynote speaker for the conference. She is the director of the Haptic Intelligence Department at the Max Planck Institute of Intelligent Systems in Stuttgart, Germany. She got her undergrad and PhD at Stanford, a PhD from 2006. She did a postdoc at Johns Hopkins, and then she was an assistant and then an associate professor at Penn, the University of Pennsylvania. Now she's, as I mentioned, at Max Planck. Her work is on haptic interfaces and haptic sensing, which she will be talking about. A few kind of highlights of Katherine's amazing career is she gave a TED Youth talk on haptics in 2012. She's received a whole bunch of honors, including the 2009 Career Award, NSF Career Award, the 2012 IEEE Robotics and Automation Society Early Career Award, the Academic Early Career Award, 2014 Award for Distinguished Teaching from Penn, as well as a bunch of Best Paper and Best Demonstrations awards. So,
thank you. Thank you, Hadass, and thank you, everyone. I'm really honored to be here and excited to tell you about some of the work that my group has done. As Hadass said, I was a professor for 10 years at Penn in the Grass Lab, and I was super happy there. It was a wonderful place to study and work. And in January 2017, I had a chance to move from this institution that was founded by Ben Franklin to an institution that had been founded only in 2011, to the Max Planck Institute for Intelligent Systems. And I wanted just to tell you a little bit about this MPI for Intelligent Systems, because it's a totally new thing. And I'm really excited that the Max Planck Society is investing in research in our field, in robotics, in AI, in machine learning. So my colleagues and I at MPIIS, we look into perception, action, and learning, both to try to fundamentally understand such systems and engineer new systems for the future. Max Planck was an amazing physicist who won the Nobel Prize in 1948. And the Max Planck Society is a mechanism by which the German government invests taxpayer money into basic research, open to application, and really focused on interdisciplinary areas that might not yet be showing up in a university. And the way they work is, I'm extremely grateful. We don't have to apply for funding. If you're a director at Max Planck, they operate by the Harnack principle. They give you guaranteed funding for the rest of your career. And it's extremely generous. And I've been there since 2017. There's a few more things. There are 84 Max Planck Institutes. Intelligent Systems is just one of them. Over 14,000 scientists. It's a huge scientific organization. It's very international, including directors like me. I'm American. I grew up in California. We have many support staff. They help us with designing, building new buildings, and all the things you have to do research. A huge budget, $1.8 billion that's coming all from German taxpayer money. Plus 10% or so outside funding. It's extremely generous. And there have been 18 Nobel laureates. I'm not sure there will be a Nobel Prize in robotics ever, but they really see this, Germany sees this investment into basic research to advance both Germany and humanity, society as a whole. And so we're located in southern Germany in the state called Baden-Württemberg. We're in two sites, Stuttgart and Tübingen, which are both, Stuttgart is a huge city, and Tübingen's a university town. The other directors, I'm one of 4 directors. So Michael Black studies computer vision, modeling humans. Bernhard Scholkopf is a legend in machine learning. I do haptics. And Metin City, who used to be a professor in Carnegie Mellon, does micro, bio, nano robots. We have the most Max Planck group leaders of any Max Planck institute in the world. And like I said, we have sites in Tübingen on the left. This is where we do more computational research, and Stuttgart on the right, which is more physical research. I also want to mention we have 3 open director positions. This is amazing. One of these was recently held by Stefan Schall, and now he's only at USC. But if you're interested in becoming a director at Max Planck, you should talk to me. Or if you know someone who you think would be a great leader, please come talk to me. I'll be here all week. One other small piece of advertising is that I'm in charge of our PhD program, the International Max Planck Research School for Intelligent Systems. This is a joint program. Max Planck doesn't grant degrees, but we work with the University of Stuttgart and the University of Tübingen to set up this interdisciplinary PhD program that I'm really excited about. and it's going super. We have wonderful students from around the world doing really interesting research, and our next application deadline is November 15th. So if you know anyone who has a master's degree or is about to finish their master's degree and is looking for a doctoral program in anything of the topics I've mentioned, please, they can come talk to me here or send me an email, and we would love to get their application. Cool. So now about my research. Many times, I'm sure, you've picked up a match and lit it and not even thought twice. We take our ability to manipulate things in the world completely for granted. But I wonder, do you think you could light a match with numb fingers? This is an epic, amazing video by Roland Johansson, who's a neuroscientist who studied the sense of touch in Sweden. He helped really understand our knowledge of the sense of touch, so go. And this is a woman who's had her thumb, index finger, and middle finger anesthetized just with an injection, like you get at the dentist. And she's trying to do this simple task that we've all done dozens of times. And I hope you see it becomes very difficult. If you can't feel where things are touching you on your skin, if you can't quite tell when contact is happening or if things are sticking and slipping, you can do it. And that's also amazing. The human brain and eye, she has full vision. It's amazing that we can compensate for this sensory deficit. But it's also, I hope, kind of gutturally or sort of deep inside you shows you, wow, my sense of touch might be more valuable than I realized. Because we're rarely deprived of it. Of course, we need vision. It helps us so much. And hearing plays a key role in our ability to manipulate and interact with the world and people around us. But our sense of touch, and specifically our hands and the kinds of mechanoreceptors, the kinds of sensors that are in our skin and all the processing, as those signals stream into our brain, there are all these low-level things happening, all different mechanical events, and our brain is able to make sense of them and give us a coherent understanding and let us control those interactions. So if I want to reach over here and open up my bottle, it's not just that I'm perceiving this object, I'm also manipulating it. And to me, that close connection between manipulation, sort of motion, and perception is fascinating and makes it kind of interesting to study. I think there's lots more work to be done, particularly because we don't understand the sense of touch, whether for robots or humans or animals, nearly as well as we understand vision and hearing. So I work in the area of haptics. I'm definitely a roboticist by training, but I work in the subdomain that looks at human and robotic interaction with things through the sense of touch. I recently co-chaired Haptic Symposium 2016 and 2018. It's a vibrant community. If you're doing anything related to touch, I encourage you to come to some of the haptics conferences that we run and to learn more. I thought I would start just by telling you kind of my view of haptics and haptic interfaces. About a year and a half ago, I was invited to write an entry in the new Springer Encyclopedia of Robotics. This is a new resource that will be coming out for our community in about 1 year, July 2019. And I have to tell you, it's a hard task to try to write an article for your whole field and try to do it justice, but I tried on haptics and haptic interfaces. This is just one of the figures for my chapter. I tried to divide the kinds of things that are going on in haptics into a few categories. I see 3 archetypal types of haptic interfaces that have emerged. These are all devices that let a human interact with either a remote environment, something far away, through a robot typically, or a virtual environment, something that's just a simulation. And we see grounded force feedback devices. This is the oldest kind, the kind that was really the only kind when I started in this field. And then we see a lot more wearable, ungrounded devices, and increasingly surface haptics, surface displays. And often, researchers in my field, as we're trying to engineer such systems and understand them, we're looking to help people directly interact with objects for inspiration and as a gold standard. For my talk today, because this is RSS, Robotic Science and Systems, I decided to focus only on the upper right part, so humans interacting with remote environments, things that are far away. And I chose this for many reasons. It's my roots. I did my PhD in a telerobotics lab, and it's also the roots of all of robotics. It's where robotics came from. This is a super old video from the 1940s. Raymond Gertz and others at Argonne National Labs were interested in how can we handle hazardous materials without exposing human operators to radiation and other dangers. And so this is actually a mechanical master-slave teleoperation system. So there's no computer involved, but there's this amazing device and mechanism and a bunch of cables that enable an operator to dexterously manipulate. This is a 14 degree of freedom, 2 7-DOF hands, picking things up. And you're able to be quite dexterous and switch modes and do other things. But you could even feel what was happening at the other end of these manipulators and do quite well. Of course, then people got smart ideas and said, I want to do this at a farther distance. Let's put a computer in there. Let's scale the motion down or scale the motion up. But as soon as you take away that physical connection between the hand and the device or the hand and the task, you lose something, kind of like that woman in the video. And I'll talk more about that. The most famous modern teleoperation system, telerobotic system, is the intuitive Da Vinci robot. I'm not personally affiliated with Intuitive, but my advisor was one of the first engineers there, and he helped create this Da Vinci. So the surgeon sits at a console, can see a 3D view. The patient, I hope you never have to go through robotic surgery, but if you do, you would be laying here, and the robot would have a long, thin stereo camera and long, thin instruments that would reach inside of you, and the surgeon would remotely control them. The tools are like 8 millimeters in diameter. They have full wrists, so they make it much more ergonomic and comfortable for the surgeon to operate. So the surgeon can just manipulate. Here's suturing. It's actually a pretty old video just to show you the kind of what the early version did. And the surgeon can manipulate things very well deep inside the body. But these systems, there are thousands of them in use. They have no haptic feedback. They're just a motion tracking system. The tools follow your movements, but you can't feel anything that's happening at the other end. And of course, surgeons can do good surgery, but there's still something missing. And Intuitive isn't the only company that makes robots like this. There are actually a bunch of competitors coming on the market soon, and I still think that haptics is an interesting challenge. Okay, so that's a little bit of the scope of telerobotics, master-slave systems. The last little piece I wanted to tell you from this encyclopedia article that I wrote was my view of what is a haptic interface. I would divide the world into, we have a human, maybe that's me, and my tangible surroundings is everything else in the world. And in that world, there may be this remote environment deep inside the patient, under the ocean, maybe something very small scale that I want to manipulate, or a virtual environment, some model that I want to manipulate either to learn something or to do some task. And then we want to create a system, an electromechanical computational system, to connect the human and their movements and their vision and their senses with that remote or virtual environment, often to give them the illusion that they're directly manipulating those objects. There's going to be a mechanical layer here. I'm a mechanical engineer. It all starts with mechanics, but we have to know a lot about many kinds of systems. We have to know how to take motions and physical interactions, like those whiskers in that last talk that you heard. How can we take sensors and measure things about what's happening in the interaction with the human and process it, compare that with what's happening in the virtual environment? So we've gone through electrical layer, a computational layer, and then bring that out through actuators for the human to feel. Maybe as the surgeon is suturing, to be able to feel the tension or feel when the tools hit one another, perhaps so they can interact in a more complete, dexterous manner. Engineered systems, robotic systems, are very complicated. And in an ideal world, everything would behave perfectly. But there are often some unintended or undesirable effects that we have to deal with. And this is often what keeps us busy. I want to make a perfect, just sense what the human did, figure out what to do in response, and do it to them. But there's often interference, like the sensors and the actuators interact, or maybe the human changes how the actuators can function, or my sensors also encumber the user. So we're always making different trade-offs and trying to figure out what's perceptible. How well can a person do? What kinds of tasks can they solve? What is needed for this particular task to enable the person to use this haptic interface to interact with a remote or virtual environment? So, as Hadass said, I became a faculty member at Penn in 2007, and my team has worked on an almost uncountable number of things. I am really honored and grateful for all the fun projects we've had a chance to work on. Sometimes we're building things from scratch. We work a lot on assistive devices for people. We work on autonomous robots to let them be better with their hands, on virtual interactions, often training. I'm doing a lot of HRI, social physical HRI these days. But for today, and of course, teleoperation, and for today, I tried to tell a story. I chose a subset of my prior work to try to tell a history only thinking about teleoperation. I titled my talk, Telerobotic Touch, so touching things at a distance through a robotic system. The work I'm going to tell you about spans from 2002, when I started as a PhD student, until current and ongoing work, 2018. Some of the systems have 1 degree of freedom and up to 14. Some are grounded, some are ungrounded. Some are more about kinesthetics, so forces and torques and motion, and a lot are more about tactile feedback, things you feel in your skin. Some of them are with experts, some are with novices, some are with everyday people, so different operator populations, and a lot of different tasks. But I wanted to sort of show you a variety of things and get you thinking. I know many of you don't do teleoperation, like it's not the thing you're passionate about. I know there are a lot of people in the room who are really keen on enabling robots to interact with the world around them more capably on their own with no human in the loop. But I would argue to you that understanding telerobotic systems well will put you in a good situation to do a good job with an autonomous robot, because the very same kinds of signals that we ought to measure and let a surgeon or a doctor or an operator feel are the same kinds of cues that an autonomous robot should pay attention to be able to manipulate its environment well on its own. And so I guess my main thing I want to convince you of, my main hypothesis or statement, is that tactile cues, things that you feel in your skin, really underpin, are fundamental to manipulation and in all these different environments and to interaction with the world. And I'm going to try to convince you that by showing you a whole bunch of different projects kind of progressing from a long time ago to much more recently. So this is me in 2002 when I had decided I loved doing research, I loved working with students. I was a teaching assistant in the machine shop at Stanford, and that convinced me I wanted to keep working with students, helping them design things. And I loved math and controls and dynamics and things. So I needed a PhD advisor. And lucky for me, I found this guy. Oops, not that guy. This guy. Günter Niemeyer, who had just joined the Stanford faculty. He'd done his PhD and postdoc at MIT, and then been one of the first engineers at Intuitive, and then became a faculty member, an assistant professor at Stanford. And I became his first PhD student, and we had a lot of fun working together. His passion was definitely, he'd done a lot of time-delayed teleoperation research. That's what he was most famous for from his PhD. And then he's on most of the patents for the Da Vinci robot. But we wanted to then think about solving problems that the Da Vinci couldn't solve and looking in other domains. And so as I showed you, this was the first, this is an even earlier version than in the video, a simple mechanical master-slave system. And then when we have modern teleoperation systems where we have a human operator holding some interface, that's usually sensors and actuators, and then we have to choose some controller to take those signals over to the remote site, make the robot do something. We have to decide what controller to use. And I'm purposely drawing a few things. I'm drawing like a 1D system. These are pictures from my own dissertation, from my own defense. I hope it's okay that I'm showing them to you today. They haven't seen the light in a while, but I still like them. So I'm thinking about the user is interacting with, just in a left-right motion, our haptic interface through their compliant body. They're thinking about where they want to move. They're interacting with a haptic interface. And ideally, I want it to feel just like they're touching the real thing. They're touching the real heart or the stone or the whatever the robot is directly manipulating, so they can use all their skills from every day and not have to worry about this messy robotic system that I put between their hands and their eyes and the task. And then over there, we have a slave robot doing stuff. It's going to feel friction and interact with the world. And so when I started in this field, I took my advisor's telerobotics class and learned about the fundamental kinds of controllers that had been designed by researchers in our field. And there are two big categories. One is a position controller. So we basically make a bilateral spring and damper between the motor of the master and the motor of the slave. And we try to tie them together as tightly as possible using proportional and derivative feedback. And it actually works really well. But it feels soft and squishy because you're adding another compliance. There's already compliance in the master and friction in the master. There's already compliance in the slave and friction in the slave. And now you're adding this soft, squishy thing between them. You're only softening what you feel. And so it doesn't feel soft. It doesn't feel hard and distinct. It feels kind of squishy. One of my other mentors, Mark Kikoski, used to call this Nerf world, a soft, squishy foam world. And it's kind of frustrating and unsatisfying, and we wanted to do better. You also, you also feel a lot of the friction. If there's a lot of friction or mass over here, you feel all of that, the dynamics. You have to push through the dynamics of the slave. So actually, this, I think, was the kind of haptic feedback that the engineers at Intuitive have tried, and many other robotic surgery systems have tried to add, but you feel, without a force sensor, just by the motor position, it's hard to deliver good quality haptics. And so typically, no haptics is better than bad haptics. And so you then just do a forward position and then nothing on the way back. The alternative, which I got really excited about, was to do a position forward and then force back. So if we can put a force sensor, if we can directly put a force sensor at the tip of my robot and let it feel the true interaction with the world, and then let's feed that back for the operator to feel. It feels really nice. You can feel so much more detail of crispness and contact. Let's say you go over a texture, but hard contact tends to go unstable. It only has to happen a few times before you think something is going wrong here. And so here is like the first little robotic system I worked with as a grad student, which was a pair of immersion impulse engine joysticks. And I'm using them as a master-slave system, forward, backwards. And there's a force sensor, an ATI Mini 40 here. And I wanted it to make it feel as though the force sensor was here, that I could feel hard contact right under my hand. There's a little angular offset, so we can touch the force sensor easily without going to an extreme angle. So this is with a feedback gain of 1. So I measure 1 Newton here. And this is with a feedback gain of 20, so raising the force up really high. With a gain of 1, it's stable. I can make hard contact, but it still feels a little squishy. And with a gain of 20, it's totally unstable. And you might wonder, well, why? Because as soon as the slave pushes on the force sensor and the force sensor starts to go up, we replay that force over here, and it starts pushing your hand backward. But remember, your hand is attached to the sensor. So that also makes the slave think, oh, she wants to back off. And then the slave comes off, and then you're still pushing, and then it goes forward and backwards, and you get these sustained contact vibrations, especially with hard objects. And I wanted to try to find a way to improve this. Could we find a way around this? Many people have worked on this problem. This is just one view. The reason there's a problem is there's this closed loop. Like, okay, I measured where she's moving her hand. I've told the slave where to go. I've measured the force. Let's say we're starting to feel force. I play that force. But the problem is, as soon as I play that force for you to feel, I'm affecting the robot you're holding in your hand. I'm causing it to move. So I get a closed loop, I get a feedback loop, and it can easily go unstable. We can analyze this with Nyquist or root locus. We could look at the stability of such systems if we can model them well. But it's kind of inconvenient. We don't want that to happen. And so we came up with an idea, my advisor and I, of saying, hey, what if I could model that? What if I could know how much a certain force that's placed here will cause the motion to happen here, and I could just subtract it out. I could just delete it. I could ignore it and make it so that there's almost no connection there. And then I can have my master interface be more of a pure measurement of the user intention, not colored by this high-frequency, messy stuff that I'm really playing. This instability is a lot like the feedback we've been hearing on the audio system when the microphone gets close to the speakers. You get it going all around. But if you had some model of how the actuation and the sensor, how the actuation affected the sensor, you could kind of get rid of it. It's a beautiful idea, and actually it does work. So here's that same system, again with a gain of 20, unstable. You hear it again, ta-ta-ta, ta-ta-ta-ta, not very nice. And now I turn on this cancellation, and I can make it, it's really hard, but so that's unstable, and now it's super firm. My hand is like, fuck. But you can stabilize this super hard contact just by thinking, I could model those dynamics and get rid of that little response. It was fun to make something work like this, but it's just a very simple system. Here it is in plots if you'd like to see that. All across the top is the without cancellation, the unstable, and as we raise the gain, as we increase the strength of the force feedback that the operator is feeling, you start to see these oscillations, and they keep going forever. And the bottom row is with this cancellation of the induced, the caused master motion. And we can estimate using a complicated model, masses and springs and dampers and friction. If we have a model of how applying a force on the robot and this includes a model of the user, will affect it, we can estimate it and cancel it out and get a really nice, smooth, solid red curve, even when the forces are high, roughly, of what the user probably was intending to do. So this was the first thing I got to publish, a couple conference papers and a journal article, or one of the first things as a PhD student. And the big insights for me were, hey, these haptic interfaces, they're not rigid. It's not really like a mass in my hand. It is flexing. There is friction. It's messy, but especially things deform. It's difficult to stabilize grounded force feedback. This is what almost everyone was working on in the field at the time, and it's still an honorable research topic, a wonderful thing, but you're kind of banging your head against deep, hard problems. It's difficult to make things stable. And then lastly, what had really enchanted me about this position force feedback was that these high frequency cues, the crispness, the texture, had a lot of information that I wanted to put in the user's hand. But I didn't want to have to deal with all these stability problems like I was having to deal with in this project. So I kept reading more papers and doing more work. And I found this amazing 1995 paper by Conterinas and Rob Howe at Harvard, where they had a two-fingered master-slave system with accelerometers on the fingertips and inverted speakers on the fingertips of the operator, so you could feel. It was just like a microphone to a speaker for vibrations. And here's the diagram of what they did. They had also a force sensor, but they were low-pass filtering it, plus an accelerometer, and they were playing that on the handle, plus a vibration actuator, so they could vibrate your hand. And not just like the buzz of your phone where a little motor goes around, but a voice coil actuator that can shake back and forth and independently control frequency and amplitude. So some great benefits. They achieved good stability and really good transparency. Everything functioned, it never went unstable, and the operator could feel like details that you normally can never feel through a robotic system. But some disadvantages where you needed both a force and a vibration sensor, and you needed this extra vibration actuator. But still, I was very inspired when I found this paper. I encourage everyone to read papers when you can have time. You can learn a lot. Sometimes I'm amazed when I read my own papers, and I was like, wow, we knew so much. They're like our archive. They're our record of what we know, and they're how we pay it back to society and the world. So read, it's important. Okay, so we came up with a variation to try to simplify how you could implement but still get some of these benefits. And there were two simplifications. We said, you know what? Let's go back to this, instead of low-pass filtering my force signal, because then I'm kind of throwing away some of the benefit, let's just use a PD controller and add an accelerometer. They're cheap and easy, and control, but use the motors on the robot that the operator's holding to output those. I call this high-frequency acceleration matching. And the idea is we can measure these accelerations in real time, smooth them a little bit, high-pass filter, invert the dynamics of the master model. So again, understanding the dynamics of the robot, and then applying a current that would cause the vibration at the operator's hand that I wanted them to feel, so that they would feel about the same vibrations at their hand that the slave was feeling at the tip, at the contact. This is a test platform that I built in my lab at Stanford. It was a pair of sensible Phantom Premium robots with accelerometers on both ones. And here's a little video of this system working. In the beginning, this is just position feedback. And the sound is this accelerometer, basically what my hand is feeling in the video. And now I'm going to go turn on this high-frequency acceleration mapping. And you can feel. It's amazing. So we have this sensor here, and we're just playing a version of that for your fingers to feel. And now this is a textured surface, and you can say again, if we do this position sort of low pass filtering, you can hear a little bit. That's actually like my fingers moving on the handle. And now we add this pathway from the accelerometer to the motor here, and your fingers can feel the texture, what's happening. If you like plots, here it is in plot form. No feedback? Feedback. It works. Feels good. So the main insights from this project were accelerometers capture really rich contact information, and they're tiny, they're cheap, they're really easy to add to robotic systems. Modeling the dynamics, though, is pretty difficult. I did only one axis, and I stayed in the middle of the workspace. And if I needed to be able to tap in all directions with all axes, it was going to get really complicated. So I knew that was a weakness of this approach. And then I also knew these were really nice robots, and a lot of other kinds of haptic interfaces you could get or might get used can't even deliver. They don't have a very stiff, nice transmission. They even sometimes have a lot more friction or a lot more compliance. And so I started thinking about a better way to solve this problem, but still, I was really proud of this. My second PhD student at Penn was a man named Will McMahon, now graduated, works at a stealth robotics startup in Boston. This is a system we built, a master-slave system. Now, these are more commodity or commercially cheap, like $2,000 robots instead of $30,000 robots. And we have, again, an accelerometer on the slave to directly measure the tool interactions, and now a dedicated actuator. So we went back to what Katherine and Hao had done. And it's important to recognize when you should change your mind, right? We should keep an open mind and be flexible and not be like completely committed to our idea just because it's our idea. And we said, hey, let's actually try this, see if this works. And we put a voice coil, so basically like a coil that can slide up and down in centering springs, and a magnet inside so we can vibrate the hand. And this is what it looks like as you're remote controlling the tool. We're measuring the signals here, and if you look carefully, this little motor is vibrating up and down to let you feel what the tool is feeling. Here's a more elaborate demo, a 3DOF demo. Again, the sound is what is heard, but now it's a left-right divide. So when you're touching things on the left, you don't hear anything. But if on the right side of the workspace, we're adding this high-frequency acceleration matching, and you can feel textures and transitions. The last part I really like, there's a little sticker that we go over that. And now here, you can even feel that little transient. This was a demo that we showed at World Haptics in 2009, and it won Best Demo there. I think just because it really showed people in their face, oh my gosh, this works. This feels good. We should do this. And it's becoming now much more standard. I was at Eurohaptics in Pisa last week, where I had a bunch of people from my team, and like maybe a quarter or a third of the haptics demos there have some form of vibrotactile feedback like this, and it's really bringing a lot more richness and realism into haptic interactions, whether they're remote with a robot or virtual or augmenting your real interactions. Again, plots, you can see there's a difference. And then we ran a big study where we brought people in and they didn't know what they were tapping on, whether it was the real surface or different variations of it, and asked them how real it felt. Higher is better. This is just a proportional spring. This is the real surface. We would slip it in there. They didn't know it was going to be a real surface. And then these are different variations of adding that acceleration feedback. We also looked at how well we were matching the accelerations with the different variations. This is like with the dynamic modeling, without, using the motors, using the voice coil. And the main thing you should remember is when you do a better job at matching the accelerations, the user thinks it feels more real. And so it's a good thing to do. But you also should see a little bit of a ceiling effect. We weren't able to get above a median rating of about a 5 out of 7. So it's clearly not good enough. And I thought about this a lot and thought, what was happening? And a big reason why we couldn't yet get up to 7 was how we were doing the feedback. You have to learn a little bit about mechanoreceptors. My favorite mechanoreceptor is the FA2, the Pacinian corpuscles. They're deep in your skin. They're a little, like a 1 millimeter diameter onion almost. And they are like biomechanical accelerometers. But it's important to understand, they are not directional. They respond to vibration in all directions, whether that little cell or little thing gets squeezed this way or this way or this way. Your fingers, your skin can feel vibrations up to 1,000 hertz in all directions, but you can't feel the direction in which the thing you're holding is vibrating. And it's important to understand the perceptual limits and capabilities of the user. And in this previous study, we were only using one axis of the accelerometer. We were only using the up and down, and we had an up and down actuator, but we were totally ignoring the transient, the transverse, the other direction of actuation. And that's something we've addressed in more recent time. So summary of this work from Will's thesis was, hey, you can do well with a handle-mounted voice coil. It's much simpler, much cleaner dynamics, much better control authority to let the user feel what we want them to feel. The quality of the overall experience is much increased if you match these high-frequency vibrations. If the same vibration is happening at their fingers as is happening at the tool, it's going to feel good. They don't have to learn any new mapping. It just feels natural and right. They know what's happening. But if you only use one acceleration axis, there's sort of a ceiling on your performance. And at the time, this is what everybody was doing. So later on in Will's thesis, we wanted to tackle a bigger problem, not just a little desktop robot going do, but something that could actually do something useful in the world. And of course, our eyes turned toward robotic surgery. And I was actually sitting in the audience at a conference in Southern California, and I had this flash of insight of, oh my gosh, we could take what Will did on the benchtop and put it on a real Da Vinci. And it worked. And it works really well. So like I already told you, you can see and move really well with a Da Vinci, but you can't, and with other robots like this, but you can't feel what the tools are touching. And tons of people are working on adding force feedback. It's really hard to prove it never goes unstable. The FDA doesn't like it when surgical robots go unstable, nor do patients, nor do doctors. No one wants it to go unstable. It's very difficult to do good, stable force feedback for a lot of reasons. But hey, what about tool vibrations? I think it's feasible and it's helpful. And I'll quickly summarize why. This is a set of components that we can take and attach onto a Da Vinci robot, different styles, and other robots like this. The sensor is a 3-axis high-bandwidth accelerometer, a MEMS-based sensor, and we add the 3 axes together. This is a problem I'm working on now. There are even better ways to go from 3 axes to 1, but this is a very good one, and it's much better than using only 1 axis. This costs like $10. We put them on the robot under where the sterile drape is, so no matter what instrument the surgeon is using, they can always feel. You touch things down here, vibrations travel up. Their left and right hands can feel some of what the tools are touching. Works for all tools. You don't have to sterilize it. We also attach actuators. Again, voice coil actuators. They're a couple $100. We attach them near the hands, and they play what the right and left tools feel accordingly. If the right tool hits something, the right surgeon's hand feels that immediately. Doesn't interfere with the robot. So now as the operator is controlling the robot and moving the tools around across the room, the instruments follow. When they hit something or when a transient happens, the vibrations travel up the shaft and the surgeon feels those cues. Here's what it looks like with a common simulation task. Again, you can hear the vibrations when, I'm going to raise the volume. So also visualize, so when rough interactions happen, like you hit something, you get nice transients. It also works in real surgery. This is an operation on a pig. This is my surgical collaborator, David Lee. This work was done by my former postdoc, Carolyn Bark, who now works at Apple, where we validated that this works really well on real surgery in a real. This is a not very bloody video, just so you know. I chose like the cleanest, nicest video for you guys, because I know you're roboticists. You don't want to see bloody things. But it works. You can measure the tool vibrations. And we also did very careful analysis. Roughly 82% of the things the surgeon does cause vibration transients that you can feel. If you're rougher, you feel more. We also recorded procedures on human patients. That's someone's stomach. This is a resident operating, but no haptic feedback to the surgeon, just measuring what they feel. Again, when there's collisions, when here the suture is getting like caught on the instrument. This is a pretty new resident. This is one of their first procedures. Now here they're trying to tighten the knot. Notice they've got their left hand off the screen. It's actually very dangerous. They could get it tangled up with something. That's a separate problem. But here, their tool is actually slipping along the suture on the thread. They couldn't even tell, but they could have felt it if we had been giving them feedback. We also took our robot on a road trip in 2013. We had a bunch of people come by and try the system, 94 people over the course of several days. We asked them, do you think this would be useful? All of them said yes. When my students showed me the data, I could hardly believe it. But then we say, hey, would you like haptics or audio? We also played the sounds, both or neither. And 2 people said they wouldn't turn it on themselves, but everybody else said they would turn it on and they wanted both the audio and the haptics. Some people only like the vibration. And they especially thought it would be helpful for training, for when new surgeons are learning. So the main results of this work, which we call VeroTouch, is that this haptic tool vibration feedback can be added quite simply. It works in real surgery, and surgeons really like it. A lot of people have worked on this project. These are my clinical collaborators. Those are all the students who've worked, and postdocs, especially Ted, Will, and Carlin. I did co-found a company to try to commercialize this. We have not yet been successful, but my fingers are still crossed. Now I have a quiz for you guys. Do you think this is an experienced robotic surgeon? Is this, okay, go. Is this David Lee, someone you would let take your prostate out? Or is, if you had a prostate, maybe you have a uterus. Okay. Is this an experienced robotic surgeon? What do you guys think? Not really, no. This is a resident. This is someone learning. All right, now I want you to watch the video again with the vibrations. That was awkward. And I want you to notice that a lot of the awkward things the surgeon or the trainee is doing cause big vibrations. They are being rough with the tools, rough with the needle. They're kind of like a bull in a china closet. And this gave us lots of new ideas about what this feedback could be good for. And this relates to autonomous robots, because surgeons were learning with no haptic feedback. They had to learn to handle these very difficult manipulation interactions with physical objects. And it wasn't beneficial, it wasn't only beneficial to let them feel, but maybe we can also assess their skill. So we did a lot of studies and showed that experienced robotic surgeons do practice tests faster and also with a lot lower tool vibrations than novices. Because even though they learned without being able to feel, they figured out how to move to be very elegant and precise with their physical interactions. This is Ted Gomez, who did a lot of this work with me as a master's thesis student. He's also a surgeon. We did a whole other set of work. This is a recent Transactions on Biomedical Engineering paper, first authored by my former postdoc, Jeremy Brown, where we took videos of people doing tasks like this. We looked at the vibrations, the force they cause, and then only based on their completion time, the vibrations they cause, the accelerations they cause on the instruments, and the force, we could rate previously unseen trials on skill on 5 different domains, as well as another human rater just watching the video. So there's enough information just in like the contact interactions of the instruments. Basically, the robot can feel how good you are when you're operating with it. It makes sense. And we can then do machine learning on those signals and rate you automatically and say, hey, you're doing really well in bimanual dexterity, but you need to work on your force sensitivity. So this was work, like I said, done by Jeremy. He's now an assistant professor at Johns Hopkins University in Baltimore. We also, I'm not going to show you unpublished data, but hopefully it will be published soon. You might wonder, how does this kind of feedback affect task performance and learning? And we do have evidence showing it helps residents learn faster and do better, but we need to publish those papers. Turns out when you're a resident, you don't have a lot of time to write papers, but I keep pushing Ted. I ping him every week, and we're making progress. Okay, so that's it for robotic surgery. Well, actually, I have one more thing, but I want to show you 2 more projects, again, pretty quick, but also related to haptic feedback in teleoperation. In my lab at Penn and in the GRASS lab, we had a PR2 named GRASP. We got it through the beta program. And I'm also interested in how we could teleoperate robots like this. Maybe it's a robot that's autonomously doing stuff in your kitchen, but it can't figure out how to flip a pancake or put the wine glass away, and it needs to call home and get someone to teleoperate it to do that difficult task or teach it some new skills. So we were interested in like really lightweight ways to teleoperate a robot, more a humanoid robot doing everyday tasks. This is part of Rebecca Pierce-Kirsch's doctoral dissertation. She did also stuff on motion mapping for the robot, and this is, but I'm only going to show you the feedback. How can we get feedback from a robot hand and give it to the operator? We wanted to use the onboard sensors. The PR2 has pressure sensor arrays in the fingertips and an accelerometer in the hand. Actually, I was lucky enough to give the early career spotlight talk at RSS a long time ago, and it was because I gave that talk that the engineers at Willow put an accelerometer in the PR2 hand, because they heard me, even back in those days, talking about how much accelerometers were great. And they're really cheap, so Willow put one in. And we were glad, because then we could use it. So we tried to mimic the making and breaking contact and the pressure sensing of the fingertips using the pressure sensors, even though they're pretty slow, and also the FA2 Pacinian corpuscles using the accelerometer. These are similar to sensors you can buy very cheap for other robots. Here's the device we built. It's a handheld wearable with a motor at the metacarpal phalangeal joint, so at the index finger base joint. And we tie that there's a geared DC motor there, and we give you grasp force feedback through that motor. We also have a pair of voice coil actuators, one on your index finger, one on your thumb. There's a complicated control diagram. I'm going to test you on this later. Just kidding. as you close your hand, if we know you're not in contact, we make it very easy to move. So we do gain switching. And then when you are in contact, we can make it much stiffer. Again, we're using position feedback, but we can kind of play tricks if you know the contact state. And then we also, so it provides good transparency. We can do making and breaking contact. I'm also a big believer in knowing your contact state. So as the user closes the hand on an object, we can move this platform over and let them physically feel contact was made and press on their finger proportional to the squeezing force. And then we can also use the same voice coil actuator to portray vibration. So for example, this is a pick up and set down. Here is where the objects hit the table. You see it makes a nice big transient that we can let the user feel so they know it's time to open the hand of the robot. It works, this master-slave controller works well with lots of objects, delicate objects, hard objects. We did a thorough evaluation using a motion tracking system and this device. People came and we instrumented the robot and its environment. People came in and their job was pick up an object, and it was in another room, so they could only see a 2D screen. Pick it up, move it over, and set it down as gently as possible. This is Naomi Fitter. She worked on this project. She's going to be she's a postdoc at USC, will be an assistant professor at Oregon State starting in next January. So you have to pick up the object, move it, and move it back. And we gave or took away all the different kinds of haptic feedback, the grip force, the contact pressure, and the vibrations. It's a huge analysis. I'll just give you some high-level, some sample data. So here we're looking at what was the peak grip force in the two different on and off kinds of feedback. If it's shaded in, it means there was a significant difference. So this one means, hey, when we turn on grip force feedback, people significantly reduce how hard they squeeze objects. Maybe that will be less likely to break them. Or similarly, when we turn vibration feedback on, they are also more gentle. They just generally become more careful. The main results were this grip force feedback worked very well. Contact feedback, not as well as it could have. And the acceleration feedback was good at helping people set things down. And then also, and this shows up also in our robotic surgery work, it makes them overall more careful. And I think it's because it increases the embodiment. It makes you really know you're wielding this big, scary, well, PR2 is not so scary, but big, strong robot, because you feel how it's moving around. And when you hit things hard, you understand that immediately. So again, this is work that Rebecca led with some other people from my group, showing you hopefully that tactile feedback can augment the kinesthetic feedback that we think about a lot more in this teleoperated manipulation. I have one more project to tell you about. I hope you're not tired yet. Back to robotic surgery. Everything I showed you so far was tool-mediated interactions, but we also wanted to think farther forward, and particularly palpation. Palpation is pressing things with your bare fingers to, say, find a lump or test the pulse or feel for a calcified artery. This was inspired because the surgeon I worked most closely with, Dr. David Lee, who's amazing. He's taken out like thousands of prostates. While I was watching him do surgery one day, he brought me an excised prostate and had me put gloves on and said, "Here, Katherine, feel this." And so yes, but it's a good experience. If someone ever says, "Do you want to feel a prostate?" you should say yes. Okay, maybe I should make no more jokes. The reason he wanted me to feel this prostate was because, unfortunately, this patient's cancer, so the reason you take a prostate out is because there's cancer inside. Cancer feels stiff. And this patient's cancer had advanced a lot since they'd had their scan, preoperative scan. And he wanted me to feel that, especially on the right side of the prostate, the cancer had gotten a lot stiffer and harder. And he wished he had known that. He could have been able to feel that during the operation and cut more widely because he knew the cancer was bigger on that side. And so we, a couple years later, created a system to try to enable that. We worked on a stationary version, then we added it to the Da Vinci. I'll just show you that version. We use a SynTouch BioTac sensor. This is spun out of Jerry Loeb's lab at USC. It's like a biomimetic tactile sensor that gives you DC pressure, AC pressure, and distribution of basically finger-shaped deformation. And its little green robot finger, we attach it to a Da Vinci instrument so you can control it in 6 staff. We attached a little fingertip display, I'll show you more in a moment, to try to recreate what that fingertip sensor is feeling. This is what the device does. It has 3 servo motors. This is super simple, but it actually works really well. So that plate can basically move in and out of contact with your fingertip and show you the tangent plane. And so then, actually this is the most interesting question on this project. Okay, I measure something from the sensor. I have some distribution of deformations and a vibration. What should I do with that device, which has only 3 motors? Here I have 19 electrodes. We also have a vibration actuator down here, like VeriTouch. But what should I do with the platform to make you feel what that fingertip sensor is feeling? It's actually not trivial. You couldn't sit down and try to model the geometry, and that you would get somewhere. But we wanted to solve it in a better way. And the idea we came up with was to have the fingertip sensor wear the device like it was the surgeon's finger. And then we could map out the whole scope, the whole range of tactile sensations that our display can create on a fingertip sensor, so that then we can use that mapping and invert it in real time while we're getting measurements. It actually works really well. We went to 39,000 different platform configurations, and at a subset of those, we tested vibration transmission from this motor to the fingertip to see how well the operator's finger would feel the vibrations and what they would be feeling. And then in real time, we search, as we're getting data, as the surgeon is pressing on something, we search for the closest set of sensations that we had during our calibration, and then we choose an average version of the motor values, and then we get the closest map transfer function and invert that to filter the vibrations. So this is what it looks like as you press the biotech sensor on objects. The platform automatically goes to configurations that would create that kind of sensation on the finger. So when you touch at the back, the platform pictures up at the back, and it's all data-driven. And it's really nice. It's kind of like pointing your camera at your TV screen to like see what your display can do and then try to map between those. We did an extensive evaluation. We had 18 everyday people come into our lab and try 3 different feedback conditions in balanced random order. Their task was to find a rigid stick that was embedded in a block, a round thing of silicone. So it's basically like a 1D search task. We had 3 different phantoms, so we could switch them out so you couldn't tell visually which one was which. And then your job was to press. The stick is in this sample video, at that angle. And I want you to watch here at the surgeon's fingertip, or the operator's fingertip. The platform makes and breaks contact and kind of lets you know the general angle. And then when you get close to the stick, it pitches up more here, right at the front. You can feel it's stiff in front. And then if you go past, it kind of kicks up in the back. So you can feel the tangent plane. You can feel there's something hard in front of me or behind me. This is just with the servos. So then we looked at the angle error with which people reported the angle of the stick. It goes down when the servos are active. That's these 2 conditions. This also has the vibrations. So we have a significant reduction in estimation error, so better identification of where the occlusion is. Faster task completion time. Significantly lower pressure, so they're going to be more gentle on your prostate if you're the patient. And also a higher overall subjective rating of the quality of the feedback and the experience. If you were watching these plots, you saw there was no difference between the S and SV conditions, but there actually was, and I'll explain. So making and breaking contact and the total pressure and the direction of contact were all really well rendered, and this deformation feedback was sufficient to let people do this remote palpation task. But interestingly, only some people benefited from the vibration, and it was the manipulation, the exploratory procedure. So a lot of people pressed, like you saw, and the vibration doesn't help you. But 7 of the subjects dragged their finger across the sample. And for those subjects, the vibration feedback let them feel the transient of where the hard thing was and significantly improved their performance at the task. So again, how you do the task, what you do, affects the benefit or non-benefit of the feedback you receive. All right, so that was work done by Claudio Pacchierotti, who was a visiting PhD student in my lab from Italy and is now an independent scientist in France, as well as with Domenico Pratachizzo and some other people from my lab. I'd like to take a moment to thank all the funding agencies who generously supported the work, especially the National Science Foundation, my colleagues at Penn and at Max Planck. And I want to thank anyone who's ever reviewed one of my papers or grants. Thank you for the helpful guidance. Many generous mentors that I've had. That's an important aspect of our career as well, and it's had a huge impact on my career, so thank you. And of course, friends and family who support us all to let us do the science we do. These are all the people who worked in my lab at Penn, collaborators along the bottom, students, postdocs. This is my new group at Max Planck, the Haptic Intelligence Department, and hopefully you'll hear more from us in the future. I do, of course, also do a lot of other work like tactile sensation for robots, physical human-robot interaction, capturing data sets of how surfaces look and feel. We had a hugging robot that was in the news. It was even on Wait, Wait, Don't Tell Me, and Seth Meyers' opening monologue. He made fun of German researchers making a hugging robot. It was pretty funny. Anytime your research shows up on television, you know you did something right. And so we're making a new Huggy bot. It will be even better, of course. And so here are just some citations of those other random things we work on. And with that, I would like to thank you for your kind attention.
Thank you so much for that talk. That was amazing. So we have a few minutes for questions. After the questions, Nate is going to give us a few announcements, so don't leave before he talks. And now we're opening it up.
What questions do you guys have for me? I see a hand here. Oh, I'll also be around the whole week, so if you want to come talk to me in a more private setting, that's good. Please. We need the orange microphone.
Hello. All right, there we go. So for the case when you instrumented the Da Vinci with the accelerometer on the top, and there was a lot of, like you pointed out that there were jerks as you touched something. Are those coming from the tool by itself, or are those coming from the fact that you put some coils on people's motors, so when the coils trigger, your hand shakes a little bit? So I don't know, like, which is the cause?
Okay, so what's the causality? So when the surgeon hits something with the instruments, let's say they hit the two instruments together, that transient causes vibrations that travel up, and then we measure them from the accelerometers. And then we condition that signal and play it through these actuators that are near the surgeon's hands to let them feel the vibration. So the causality is sensor measures something that happened, and then the surgeon feels it and then is aware of it. We don't get closed-loop instability because there's good frequency separation. And you can't move your hands fast enough to like make the motors, the voice coils, vibrate. Do you want to ask a follow-up question? Did I answer your question?
Kind of just follow up on that. Is there a positive feedback loop going on?
In Veritouch, there's no positive feedback loop. We've never seen it go unstable because we do frequency separation. So we high-pass filter these signals around 80 hertz, I think, and up to 1,000 hertz. And then we play only that frequency range. Your hand can only move back and forth at a few hertz. Actually, there's really good really good encoders on the Da Vinci, so it can measure very fine motions. We originally used from 20 hertz to 1,000 hertz, and we found we could occasionally make the robot go unstable, because if you got some low-frequency vibrations, it would shake the surgeon's hand enough. But another disadvantage of that wider frequency band was you felt a lot more of the robot's ego vibrations. And so we were able to solve kind of two problems at once, like increase the frequency separation by throwing out the 20 to 80 hertz information, and you also then don't feel quite so much of the robot's own like rant, 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 rant. So you get better like clarity, better foreground, background contrast of the contact events. Thank you. What other questions do you have? Here in the front.
So yeah, amazing talk. There is this urban legend that, you know, computer vision was once transduced to the back by a bunch of needles. I don't know whether it's true or not. But
I think it was vibration motors, but yeah.
So I'm wondering whether you have to actually transduce the actual fingers. Can you sort of somewhere else actuate and learn the feedback, you know?
Absolutely. So the things you're talking about are more like sensory substitution. So if we have, say, someone who has impaired vision and we want to let them see with their skin, you can take visual information and map it onto the skin. But your skin isn't really adapted for that, so it probably will take some learning and practice and some good design. Actually, last week I felt a really nice demo from Hong Tan's group at Purdue, where they're taking phonemes and playing them through your arm, and they have people who know hundreds of words of sort of hearing through their skin. It's not an area I've worked on particularly. I've been more focused on actually recreating mechanical interaction, sort of task-based. But this is an interesting and exciting area for assistive technology. Haptics has many potential uses, including this. We have another question here.
Hi. So you focused mostly on the teleoperation aspect in this talk, but there's more and more work in simulation and robotics, and of course there's VR. So I'm curious, how much haptics can you achieve in VR with a wireless controller or maybe even a phone, for instance?
Great question. So I keynoted at IEEE VR a couple months ago, and there I only talked about VR things, and I didn't talk about any of that here. I tried to keep the two talks totally different. I think it's archived online, but you can do, let's see, I'll relate to this. So you've heard me talk a lot about that vibrations are important for textures. So my group has also like modeled tool-based interactions with textures and hard contacts and built like digital representations of that. And we can put that in VR with like a little fingertip wearable or a handheld device with vibration output that's broad bandwidth, not just buzz, but that has independent frequency and amplitude. And other people are doing this too, and it adds a lot, and it's lightweight, it's low cost. Then fingertip contact, making and breaking contact, similar to like this or this, is more complicated, but also has probably some benefits, especially if you're grasping and picking things up. But yeah, I see mostly tactile cues. Other people are doing even more advanced things. Oculus Research is investing a lot in this area. One of my PhD students is going there for an internship. They've hired like 100 people in haptics to try to do haptics for controllers. I'm sure it's coming.
So there was a question up there. There are microphones on the sides, so we're not going to throw things up there.
Yes. I can't, but I mean, I can repeat your question. Can we get the microphone on the balcony?
So you didn't talk much about latency. Can you tell us what are the limits on latency for this sort of work, and what are the limits of what we can sustain with latency?
Yeah, so time delay isn't a big focus of my work. It's something my doctoral advisor and others in my lab at Stanford and others in the field look at a lot, especially if you want to do long-distance teleoperation, so into space or orbit or deep underwater, you might start to get just a transmission time delay. You have to, that creates a lot of stability issues, so because then the feedback is coming late and can do work on you in the wrong direction. It can do positive work on you, even if it was supposed to be dissipative. But if you keep things stable using various tricks, maybe up to 100 or 200 milliseconds delay, the operator won't notice, but beyond that, it's not a smooth interaction anymore. I am definitely focusing on things in the same room without a big time delay, but it creates lots of interesting, but some key application areas require good work. I have a visiting PhD student in my lab who's working on haptics for a needle insertion on the space station, and there we're starting to think about time delay. I see a hand here.
Hi. Oh,
hi.
I know for certain power tools, sometimes there are constraints on how long you can use the tool due to vibrations imposed on the hand. Yeah. And I'm wondering if that's all a consideration for long duration surgeries.
Great question. So the vibrations that we cause in, say, VeriTouch or any of the other systems I showed you are of the same level and magnitude that you would get just using a hand tool, like a laparoscopic tool, or directly maybe using some sort of metal glove picking the object up. So they're not like sustained, unless you were using the robot to operate a power tool. And then, yes, the vibration transmission would probably start saturating your mechanoreceptors or feel not very nice. But we actually often would ask subjects, are there any unpleasant sensations in your hand? But no, and they don't even have to learn what the signals mean or kind of get irritated by them because they're just so natural. You almost don't even realize they're there because we're bringing back a connection that should be there and is missing. But
thank you.
You're welcome.
Last question.
Hello.
I'm not sure if this thing's on, but I had a question if you've ever explored neural networks for more realistic haptics.
We are using neural networks in my lab. Currently, I don't actually find that the quality of the haptic feedback we provide is particularly limiting, or the signal itself is the limiting factor. I think more the hardware and like sensing has been more the limiting factor, but certainly we could probably use neural networks to learn an even better model. I think others have already done that for texture. My group did a lot of work on what we call haptography, the haptic texture rendering. And if I remember correctly, I think Seung-Moon Choi's group in Korea has used neural networks to make even better models. I don't know yet if they're perceptually better than the more simple models that we've used. But certainly, I think deep learning has a role to play, especially for synthesizing accurate, interesting signals under different scenarios. All right.
Thank you so much.
Thank you.